Hello everyone, and we're back. Today we're going to take a look into two different implementations I coded of a sparse segment tree. I will explain sparse segment tree, what it is, why do we need it. But first I want to tell you guys that more videos are coming. Technique on a tree, on trees is coming. One very interesting technique on DSU is coming, video about it. So please click that subscribe button, check out my previous other content, and yeah. So let's one of the segment trees, one of the sparse segment tree. I'm going to code it live right now, and I will show you another implementation, some kind of alternative implementation, and why actually this alternative implementation can help you reduce memory. So first, here we have this problem of range sum query. So this is the problem where we need this sparse segment tree data structure. So the problem actually requires us to build a data structure such that two queries are possible. So assigning to a cell I some value x, and then finding the sum of integers on some segment from L to R. But you will notice that this can be done with an ordinary segment tree. So why a sparse segment tree? An ordinary segment tree, you can have a point update. We're not going to talk about lazy propagation today. In the next video, we're going to implement on the sparse segment tree. We're going to implement lazy propagation, but right now, not. So what's going on here? On the ordinary segment tree, we have a point update, so we can update one point, one index, one element in the array, and then we can sum up from L to R. But if the array is bounded up to 10 to the 5, something in linear time, so linear array, let's say. But here the array can have up to 10 to the 9 digits. So what's the idea here? If you have something with such an enormous amount of not digits, elements, right? So 10 to the 9 or 10 to the 18 elements, you cannot store them in memory. That's like gigabytes of memory. I don't know, but so 10 to the 9 you can store it in memory, and 10 to the 18 no chance. But you can store only elements that you need. And there will be only 10 to the 5 elements that you actually need, because they're at most 2 times 10 to the 5 queries. So 200,000 elements that you actually need, right? Okay, so we can store these elements, but you can say that, okay, I can do index compression, and I can compress all the indices beforehand, and then I can use ordinary segment tree. Yeah, for many problems you can do that. But this problem here requires you to online query. So there are these here that depends on the answer. So the query index actually depends on the answer. And this makes the problem harder, and it requires this kind of lazy segment tree. Not lazy, sparse segment tree, right? So an ordinary segment tree is a very common data structure. An ordinary segment tree is just, let me just draw that. So an ordinary segment tree is when you have like some array, and then you kind of divide the array into, so the one of the node here covers the whole array, and then you divide by two nodes covered like the half, each half, and then like that recursively, right? And then when you cover the whole array, then you can, if I want from this segment to query something, I have to merge only this node and this node, and thus merging only takes logarithmic steps. So if I want to cover this segment, let's say, then I will merge this node and this node, and this covers the whole segment like that. I won't actually care about these two nodes, because in this node it's the answer of this segment. So we all know how proper segment tree works. But what's the difference between like a ordinary and a sparse segment tree? So you could have a lot of elements here that are all like zeros. So like all of them are going to be zeros, or some identity element that we're going to call default. This default element is going to be all zeros. In fact, I will explain further on how I code this, but just bear with me right now. So if I change an element here, let's say I change this element, what I only need to update is some logarithmic amount of nodes up to the top here. I don't actually need to store any of the other nodes. So this node actually stores the element. This node will store the element, and this node will be responsible for the interval about the element and here, like that, like one more node. This node will be responsible for this interval. This node will be responsible for, let's say, this interval, and this node will be responsible for the whole array. Just like in the segment, in the ordinary segment tree, we just don't store all of the other nodes. These don't exist here. Okay. So we need a hierarchical data structure with pointers in order to achieve this, because we're not going to create all of the nodes in our array. We're going to dynamically create nodes that we need. Okay, so let's go code it so you guys can have a better understanding of what I'm talking about. This is the code with like that solves the task. So we need to implement this update function and this query function here. Other things are just not important. Okay, so let's. So I always start with getting this kind of structure. So a tree structure, and this I will always have a pointer left and pointer right. So this will point to the left and the right node. First, they will be initialized to null pointers because there will be no nodes there. Then I will have a low and high value that this will say what interval is this node covering for. But this interval will be from the low side will be inclusive, but exclusive from the high side. So the low side will be maybe it's going to be better if I code it like that, maybe. Okay, so zoomed in a bit more. So inclusive from the low side and exclusive from the high side. Why is this? This is because it's easier than to code the boundaries on the checks. So if the checks, I'm going to come to there. So one more thing, I coded initially these segment trees with an I template, and then you can put here template type name I, and then this I template will be like, you can say that this is for example an integer, or this is a long, because sometimes if you're working on a task which can go up to 10 to the 18, you may want to change this low and high to a long. But for now I will just put it in, because I think I will confuse you more. For some of you that are not familiar how templates work. Templates are not runtime things. Templates are purely compiler. When the compiler compiles, it already knows what is this template. But let's just don't go there. Okay. Then I will code another structure here, data, that will call that this structure will actually contain the data of the node. Here you can have multiple things in some nodes, because some segment trees require to not just only have the sum of the nodes. Let's say then you can have the max, the minimum, or the product, or a product module or something, or whatever. You can have anything here in the data of a node. For now, I will just I will just say value, and this is just some equal to some default value, which I'm going to say this is 0. Okay. This data I have to add it here in the tree, and then we're going to talk about something about memory optimizations here. what you can do when you're in a contest thinking about memory, but for now I'm just gonna leave memory alone. I won't care about memory. Okay, then I have to implement an update here, and the update will take a new data, so let's call it X, and will just update my value. So the update to the value depends on the task. Maybe sometimes you want to add on the value, maybe sometimes you want to do some job, something, but this will update the value of a specific leaf node. So this is the targeted pointed node. So this is one node. This will update on one node, the end of the chain, the leaf node. This won't update something upstairs because we're not doing lazy propagation yet. So the value is, I'm just going to copy it from the X value. I'm just going to set the node. So I can just do anything. I can have like plus equal here or whatever, but I will just set the node for now. It's just easier to do. And the task actually requires the setting of the node. So here it just assign the cell I the value X. Okay, so let's go further. One thing I code is, I think so the thing is here that you can have multiple types of implementations of these sparse segment trees, however you like and however the task actually requires. But what I did with my other segment tree, and why I do this, is because I want to modify this data structure all the time and just don't care about how the segment tree actually works. So even if you don't know how the segment tree actually works, if you just can modify this data here, and this will actually give the power of the segment tree to you. You don't have to know the other functions that we're going to implement downstairs. Okay, so we need to update a node, and we need one more function that will merge two nodes into one node. So two known values, it will merge them on a level up. So I will make this function static. It will return a data, so new data, and I will call it merge, and then I will say, okay, I get data A and data B, and now I have to merge them. And actually I will just return some other, so this is data, I'm returning data, but actually here I will merge the value A plus value B. So that this is saying I will return another this data here, struct, but with a merged A plus B. And that's it. That's all you have to do. Okay, let's go and create actually the string. The constructor of the tree will have left and right. Okay, so left and right is just, we'll say that low is left and high is right. So this is what kind of interval does this node actually encompasses. Okay, then I will have a destructor, because many problems can actually you can have many tasks, subtasks in the problem, subtasks, and then you have to delete the tree. So how you're gonna delete the tree is just going to call delete L and delete R. Okay, so this is what we're gonna do. Okay, now that we have this, we have to work on the update function and the query function. So the update function is pretty straightforward. It will take an index P, let's say the position P, and will take a value X, some data X that we're going to update into that P, right? And here the two most important checks that we're going to do. First check is going to tell me if actually P is not in that interval. So how do we know that? We know that by saying if the right of P, so my right of P, and I will explain why I do that in a moment. Okay, maybe it's not really understandable, but what is saying here? It's saying if P is above the high, So remember, high is exclusive here. Remember that. So P is inclusive. And it says if this is exclusive, so this is let's say 3 and this is 3, then P is not even in that interval. So P is just right to that interval. It doesn't affect that interval. On the other side, we need to add P plus 1 for that low. And what you can do here is you can say R is P plus 1, and you can change R here. And I will tell you why I'm actually doing this, because in the lazy propagation video that is coming up, this will actually be R. So R will be actually you will have here int L and int R. Okay, but for now I will just say it like this. And now you have one more check, and that's if it's totally inside that interval. So if this interval is totally, so if my interval is totally inside the interval that the P, so this actually, what actually this is going to tell me is it's going to tell me that I need to set this node, and this is P right here. Okay, so this will be I will have to update myself with this X, right? And then I will return. I know that this is done. Okay, this is excellent, right? As far as I'm concerned. Then what happens if I have to go down? So if nothing of these two is satisfied, then I have to check if actually my children are ever created. And that's why I create another function called push. And in the next video, again, with lazy propagation, this is all going to become a lot more understandable why I'm doing this push function. But this is just a function that will create the children if they don't exist. And the push function, first I have to check if I'm the only, here what I'm checking is if I'm the node responsible for a single element in the array. If that's the case, if I'm the node responsible for a single element in the array, I cannot have children. Okay, this is a leaf node. It just cannot have children. Okay, and another thing is if they're already children. So if L is like already exist, then I don't have to create the children. And how I create the children is just low plus high minus low divided by 2. And now here is another fact. Here is another thing, another design choice why I'm doing this. Why not just low plus high divided by 2? It's because low plus high divided by 2 can overflow. And this is much more safe. So this is safer. This high minus low just divides by 2 first and then adds to low, and this cannot overflow. Okay, so this is the midpoint. We get the midpoint, and then we create the two children. So I create them instantly, the two children, even though I don't need them, and I will show you in the next implementation how the memory is saved if I actually don't create the two children. But that's for the further in the episode. Okay, so we have this. Let's create the two children. So left is new tree, and the left is going to be from low to mid, and the right is going to be from mid to right. And that's why I'm telling you that this is very good, the inclusive and exclusive, because you don't have to worry about here mid plus 1 here. You don't have to worry about, it's just low, mid, and mid high. It isn't plus 1 nowhere. It's plus 1. It's just, and here it's really understandable what it does. It's both of the rows are the same. Here are like different operations, and here is just like swapped. It's just very easy to get your to wrap your head around this. Okay, so we create the two children nodes, but we need to call this push function, right? And then we say, okay, we are going to update the left node with the same thing, and I'm going to update the right node with the same thing. So one of these will be affected, but the other will just terminate. Will just it's called like a dead end node. It's just, it will terminate like that. And then I'll call a function called merge. And this merge function, what it will do is just merge the two nodes into the answers of the two nodes into my node. The answers are going to be so D is going to be data. So this is the static data. So this is data merge, and this is going to be left data and right data, and that's going to be it. You can now here, for just the sake of this, I will just, if there are no children, I won't do that. But this function won't be even called if there are no children. So I could possibly leave that out. Okay. Then I want to have a query function, and this is this is we're at the end, so I promise. The query function will return data, because data you can query sometimes multiple arguments, not just the sum. You can query minimum, sum, maximum, and product at the same time, and I wanted to be able to do that. And then these things are the same here. These things are the same. You just code it exactly the same. So if it's outside of the interval, we just return an empty data. If it's totally inside the interval, so we have to return myself, the data here. It's very easy. I have to push in case that I need my children nodes, and then I will say data merge I will query into the left node on the same interval, and I will query onto the right node on the same interval, and that's it. That's all I need to do as far as I think. And then I need to create this tree, and then I need to update. Let's see if it works or if I have missed something. I don't think I have missed something. No, it works. It should pass. Okay, let's now submit it, and you'll see it won't pass, and I will tell you why. Submit it. Okay, let's just okay, and you see accepted, and then memory limit reached. Oops. Their tests are really good on this task. I will share this task on the in the description. So why is memory limit reached? I will explain very briefly. It's because when I'm going down, I actually need to update. Let's say I'm going down and I need to update this node, right? And I always create nodes, but I always create one more adjacent node in which I never use here, like that. So when you now update once again, this node here probably like updates like some adjacent node here, and then it just again creates a lot of unnecessary nodes. For each node down the layer, it creates one more unnecessary node. And okay, you see, I mean, yes, if you have like 512 megabytes, it would possibly work. But okay, so how do we optimize this? I will show you this here. I already wrote. I will just go through so you know how to optimize this when you're coding. If you see that this is the problem in the sparse segment tree, then you can optimize with this technique. So the thing here is to remember is that okay, I'm not going to create both of the nodes. I would create only the one that I need. the left or the right node. And in the update function, it's the same. I return if that node does not cover my interval, I just return. If that node exactly covers my interval, I update it. And the midpoint, I find the midpoint. And if it's on the left, if the point I want to update, it's on the left of the mid node, I only care about the left node, the left child. Otherwise, I care only about the right child. And if the left child doesn't exist, I will create it. And then I will update the left child. But I will only update the left child. I won't even care about the right child, because I will know that there it won't happen. There would not happen. Okay? The right child as well is the same thing. Just remember here to swap low, mid, high. Okay? But then when you merge, it's very important to check if the child is actually existent. Then you will take his data. Otherwise, you will take an empty data. And in the query node, I will check here that if the two children are existent, I will go query both. But if one of the children only exists, I will query the left children, and I will query the right. I will return the right children if the right children only exists. But what happens in the sum query here, where a plus b, it's totally perfect, totally fine to write this, and this will get accepted. So if I copy this and I go into this and I submit to the solution, of course choose C++ 17, this will be accepted with something around 120 megabytes of memory. Okay, the queries are a lot, so you can see that it's quite okay. And I'm not even using sync with IO. Don't sync with IO. It's fast enough. It's very fast. It's 400 milliseconds. But there is a huge problem with this implementation. In case that the data here, the data is dependent. Sometimes you will have queries such that the data is dependent on the size of the node. You have to think about, so imagine if the data calls in for like a node that has 10 elements in, you have to multiply this by or sum up or like instead of zeros have like ones, and then you have to do 10 plus 10 times 1 or some lazy propagation. If this is to happen, then you cannot merge it like this. Then you cannot simply merge it like this. Why? Because on the left node here, when you, for example, the right node does not exist, when you return the left node, you have to return a right node as well, but with the proper amount of size, the proper size, right, of the right node. Even though it's empty, you have to have it there. And if in case you want to do that, so in case you want to do that, this data here is actually going to be like, if we have a constructor data here, let's say we have a data constructor that will take left and right, and let's say that there is a parameter size which is right minus left of the node, and then there's like size, something like that. Okay. If that's the case, then you want here in the data constructor, you want to the left node will have exactly size low and mid, right? And the right node will have mid and high, right? That's the size, even though they're both the same, but I'm just gonna ignore that. Okay, and then here in this here thingy where I don't return anything, I will just maybe have like a constructor that does like size. I mean, I will have like default constructor here as well, so this will work. And then when I merge the two nodes, if the nodes exist, it's okay. But if the nodes do not exist, one of the node has to be changed. So it has to be again merge the left node, but the right node here will have like the data, a data node which will have low and mid here. Just do this, and the right node again. Now I'll just reverse this. Why here? It's sometimes it's very important to get the right. So left, right, and left, right in order, because some queries do take everything in order, are not commutative. And this will be like, this will be low and mid, and this will be mid and high, because this is the right node. But now high is not defined, mid is not defined, so I'll just define mid here. And this will act totally the same, so this should act totally the same. Okay, so this here actually the size has to be combined now, because the size combines as well. And now you saw how even this merge is possible. So it's just you have to change like probably one line of code to get a task working here if you have this kind of data here struct. Okay, what else do I need? Yes, okay, so this here is like, yeah, size 1 doesn't really matter. What else do from long to 8? Yeah, so the constructor here, I'm just going to do data d, and d dot value is b. Also, data is inside the tree. Yes, inside here I'm using templates, that's why they don't. Okay, what else? Warning, conversion warning. So, oh yeah, so here as well, when you're merging and you have multiple constructors, try to create the data first and then say value is equal to a.value plus b.value, because this will actually call the second constructor and will put up a warning, so you know that this doesn't match the second constructor's types. That's why you have to be careful with these things. So let's say like this, and then just return the like that. And now it passes, and now even though I have like one more variable size, I think this should be this should not take a lot more memory, probably. I don't know, we'll see. Maybe the size will, yeah, okay, it passes still with it probably the compiler optimized this size because it's never been used, maybe somehow. I'm not sure, because the same memory usage is seen as before. But this is actually how you write a segment tree, an optimized sparse segment tree. So ordinary sparse segment tree that is very easy to write, this is just few lines of code, or you can write this optimized segment tree where you just have few more checks here, essentially, few more checks in order to pass to make it a bit more optimized. And you only need, if you have these implementations, which I will probably post them on GitHub, you only have to change the data here, so how you update and how you merge and what you store in the nodes, and this will automatically just work. You want like the update and the query will work regardless of the problem. You just have to change the data here and just use it, the segment tree, even though if you don't know how to use this, how to use a segment tree. So this is going to be, this is already a very long video. Thank you guys so much for watching, and I see you probably in the next one, maybe explaining DSU, maybe lazy segment tree. Just click that subscribe button again once more, please. And yeah, thank you so much for watching.